I'm holding this ball bearing on the rim of a hollow bowl. If I release it, it will roll down the bowl under the influence of gravity. Now, I'm interested in what the motion looks like when seen directly from above. If this were a spherical bowl, you'd have no hesitation in saying that the ball would roll down through the bottom and up the other side. And seen from above, that would be a straight line motion. Well, to see if that's what we've got, I'm going to place two ball bearings at diametrically opposite positions. And I'll release them simultaneously from rest. Well, the balls didn't collide. They moved around the bowl and they gradually slowed down. They slowed down because friction caused them to lose energy. But it's easy to see that they don't travel in straight lines. They're continually changing their direction. And that's an important property of this bowl. Now, we've constructed this bowl in an attempt to illustrate how a particle will move if its coordinates across the bowl satisfy this pair of linear simultaneous differential equations. And this program is about these equations, how we solve them, and what their solutions look like. Now, I'm not claiming that the motions you've just seen are exactly given by these equations, and there are several reasons for that. First of all, there's friction in the bowl, and then this ball bearing is spinning, so it's not quite a particle. But most important of all, it's very difficult to build a bowl of exactly the right shape. So, as well as the physical model of these equations, this bowl, we've also built a computer model, a sort of fabulous perfect bowl, which will show us how a particle would move if its coordinates obeyed these equations exactly. That's a surprise. Even though the motion wasn't a straight line, the balls collided. What would happen for a single ball? For the same point on the rim, the ball executes this sort of motion. There are some obvious differences. Without friction to slow it down, there's no reason why the motion shouldn't continue forever. The ball traces and retraces the same path, and that's very different from the bowl. Is it a fluke? How about a different starting point? The path is different, but there are still similarities. The basic shape, 3 sweeps across the bowl, a momentary pause, and then back again, that's still the same. And it's still the same for this starting point. These paths, we call them orbits, are nothing at all like the paths in the bowl, and that's part of our story too. But still in the perfect bowl, what do you think would happen if we started here? For this starting position, we simply get a to and fro oscillation along this straight line. Well, actually, that straight line motion occurs in the real bowl as well. Although the ball bearing's losing energy, its motion is clearly confined to this direction across the bowl. Its motion is simply a straight line, orbit, in this direction. Well, that's interesting, but it also raises some questions that we're going to try to answer in this program. First, can we find the directions in which the orbit is just a straight line? I mean, can we predict those directions from these equations? And second, can we find all the orbits in the computer animation in that fabulous perfect bowl? And third, can we begin to understand what's going wrong with the real bowl? Why is it so different from the animation? Well, to get anywhere with these questions, we want to start with the equations. Bob.
Okay, let's look at the equations. Here they are. Now, you may wonder how these equations relate to John's motion in the bowl. Well, what I've done is I've chosen x and y axes as shown, And what those equations do is to tell me the acceleration that an object would have if it were at a point x, y in the bow. The top equation tells me the acceleration in the x direction, and the second equation, the acceleration in the y direction. I'd like to say a couple of things about the form of the equations. Notice they're both second-order differential equations, and these terms on the right-hand side are linear, so we have linear differential equations. And what's more, they're homogeneous equations. There's nothing there that doesn't involve x or y. Now, we'd like to solve these equations. That's to say, we'd like to find x and y as functions of time. How might we do that? Well, having noticed that they're linear equations, I could try treating them as if they were linear algebraic equations. For example, I could add them together or subtract them. Now, in this particular case, that gets us somewhere. Although it's a bit of an accident, it does depend on the special form of the equations that we have here. If I add the equations together, I get this. That looks nice and simple. If I subtract them, I get this. In this equation, we have the second derivative of x minus y equal to a constant times x minus y. That's to say, the second derivative of a quantity proportional to that quantity with a negative constant of proportionality. And that means that we have the equation describing simple harmonic motion. And having recognized the equation as that, I can solve it. I can just write down the solution to a simple harmonic motion equation. So the solution for the variable x minus y is just this. I'd have to work out that constant omega. In this solution, the constants c and d are the arbitrary constants. They're the ones that depend on the initial conditions. And there's one particular thing that I can see now. If the initial conditions were right, then I could achieve c and d both 0. If the right initial conditions, we'll get those values for the arbitrary constants. And that'll mean I have a solution of this form. That's to say, a solution in which x minus y is always 0, in which x is always equal to y. And that will be motion in a straight line, the straight line x equals y. And I reckon that's what John found.
Well, yes it is. Here's my x-axis across the bowl, and here's my y-axis. And this is the direction where I found before a simple backwards and forwards straight line orbit. And with these axes, that's just the line x equals y. But Bob's other equation also leads to a prediction. In fact, it predicts we'll get a similar orbit in the direction x plus y equals 0 or x equals minus y. And that's just here. Another straight line. It works. So, with these equations, simple addition and subtraction leads fairly directly to these two straight line orbits. But if I had different numbers on the right-hand side, adding and subtracting really wouldn't help me very much. So what I really need is a procedure that's going to work every time.
You'd like a procedure, John? Well, a procedure is by no means obvious. I suppose I could try treating them like linear algebraic equations. That helped before. Now, with linear algebraic equations, I can write them in matrix form. Could I write these differential equations in matrix form? I can. Here, I've written the equations in a matrix form. Let's just check that this is right by multiplying the matrix out. If I do that, I get minus 5/9 x plus 4/9 y is equal to x double dot. That's just my first equation. And the second equation comes from the second line when I multiply out the matrix. Well, that's one way of writing them in matrix form. I could also write them just like this. Now, I've denoted by capital A the matrix. And I've used vector r to denote the vector x, y. The transpose is just there to note that we mean a column matrix, x, y. And I've used r double dot to denote the vector x double dot, y double dot. Okay, I now have my equations written in this compact matrix form. And the form is interesting because it looks very much like the simple harmonic motion equation, which showed up before when I was just playing about with the equation. Maybe that gives me a hint as to how I might solve the equations. But before I try and use that hint to solve these equations, in which the variable is a vector and the constant of proportionality a matrix, I think it might be a good idea to remind ourselves how we have solved the ordinary simple harmonic motion equation. John?
Let's consider how we'd solve this equation. Now, you solve this by trying a solution of this form, a constant times an exponential. Differentiating once gives us this expression for x dot, and differentiating again gives us this. Now, our equation connects x double dot and x, and using our expression for x double dot, we can rewrite this equation as this. Since an exponential's never zero, for this equation to be satisfied, we must have lambda squared is minus 9. Once, this negative value for lambda squared might have bothered us. But we now know that the complex solutions, lambdas plus or minus 3i, are going to give us the periodic motion that we expect. Because there are two values for lambda, our general solution is the sum of a constant a1 times one exponential and a constant a2 times another. Well, written like this, the periodicity doesn't show up. But we can use what we know about the complex exponential, that e to the I theta is cos theta plus I sine theta, to rewrite our solution as this, the sum of sines and cosines. So, to solve for simple harmonic motion in one variable, you try an exponential, substitute it in, and get a general solution in the form of sines and cosines. Is that any use to you, Bob?
Well, here's our equation. And John suggests that I look for a solution of this exponential form. Now, in my case, my variable is a vector. So I better try something that's a vector, and I can do that as long as I make a vector. Okay, to try that in the equation, I'll need to work out the second derivative, r double dot. Fortunately, I can differentiate that variable vector r just as if it was a scalar. And this is what I get. The only thing that's varying is e to the lambda t. And when I differentiate that, I get lambda squared e to the lambda t. Now I substitute back into my original differential equation. So I get this. There's r double dot equals the matrix A multiplied by what I'm trying for r. Now, e to the lambda t is never zero, so I can cancel that. And that just leaves this condition. So what I've shown is that this is a solution of my differential equation just so long as the vector A and the constant lambda satisfy this condition. But what about this condition? I hope you recognize it, because it's nothing more than the definition of eigenvalues and eigenvectors. What it says is that the vector A is an eigenvector of the matrix A, and that lambda squared is an eigenvalue of A. So I've shown that I have an equation, a solution of my equation of this form, just so long as A is an eigenvector of the matrix A and lambda the square root of an eigenvalue. So what are the eigenvalues and eigenvectors of the matrix A? I asked you to work them out before the program, and here they are. The eigenvalues are -1 and -1/9. Corresponding to eigenvalue -1 is the eigenvector 1 minus 1. And I could multiply it by any constant, and it would still be an eigenvector. For the eigenvalue -1/9, the eigenvector is 1, 1. So what does this give me in the way of solutions? Well, remember my solution was A e to the lambda t. A is the eigenvector. That's the eigenvector for the eigenvalue -1. And I need e to the lambda t with lambda the square root of -1. Well, the square root of -1 is I and minus I. But I don't like complex exponentials any more than John did. And I can replace them in just the same way as he did with sinusoidal functions. And that's what I've done. So, now I've found two solutions of my differential equation. What do they tell me in terms of the motion? Well, let's look at one of them. This says that the position is equal to a constant vector multiplied by a sinusoidally varying scalar. So the position is always going to be in the line of that constant vector, and the motion is going to be some sort of simple harmonic motion in a straight line.
Bob's eigenvector result just confirms what I found earlier by experiment. The eigenvectors of the matrix A are 1, 1, that's in this direction, and 1 minus 1, that's in this direction. And Bob's shown that these are the only two directions along which we can have a solution e to the lambda t times a constant vector. So these two eigenvectors correspond to the two directions along which we can have oscillatory motion in a straight line. Well, we've got so far, but that's only really two very special motions, motion either along this line or along this line. And I'm not really very impressed by that, because I've seen very much more complicated motions in the perfect bowl and also in this bowl as well. So how about that, Bob?
The reason I haven't got the general motion yet is because I haven't yet got a general solution to my differential equations. But I've got one here. I'll remind you in a minute how we got there, but here it is. All I've done is to take one of the terms that I had previously and add to it the other term that we had before. So the general solution is just the sum of my two previous solutions. I can add together solutions because I started off with linear homogeneous equations. It's similar to a lot of other problems that you've seen in the course. Of course, I've not proved that, and nor have I proved that what I've got is the general solution. But we've got a hint that it might be if we look at the number of arbitrary constants in the solution. There are 4 here, 2 C's and 2 D's. And I started off with 2 second-order differential equations, which suggests that I might get 2 times 2, that's 4 arbitrary constants in the general solution, which is what I've got here. Now, earlier on, John asked me if I could find a general procedure for solving problems like this. Well, I've got one now. Let's run through it. First, you write your equations in matrix form. Now we concentrate on that matrix. this is where most of the actual work is. First, we calculate the eigenvalues of the matrix. Then, we calculate the corresponding eigenvectors. In this case, the eigenvalues are -1 and -1/9. And the next step is to find their square roots. Well, the square roots of -1 are plus and minus I, and the square roots of -1/9 plus or minus 1/3 of I. And now we've got enough information just to write down the general solution of our differential equations. You write down the eigenvector multiplied by a sinusoidal term that's determined by the eigenvalue. Here's the other term from the second eigenvector. There's the eigenvector, and the 1/3 here comes from the 1/3 I in the square root of the eigenvalue. So now I have a general solution for the problem we started off with. And that general solution is obtained just by adding together the two solutions I was looking at before. So that should tell us something about the motion. It suggests that the general motion is found by adding together those two particular motions that we were looking at before. Is that any use to you, John?
Before I can say whether it's useful, I've got to see what the solutions look like. So, back to the perfect bowl. Here, the motion is along one of the eigenvectors. Here's the motion, with a different frequency 3 times as fast, along the other eigenvector. Bob's general solution is the sum of these. Here's the ball. Let's start things moving again. Now, that's the motion we saw to start with. The axes aren't important, it's the eigenvectors that matter. Starting here, we get this. And here, we get this. This is behaviour for the perfect bowl, where the ratio of the frequencies is exactly 3 to 1, as we had in the general solution. But what about the real bowl? Well, one of the things that is difficult to get right is the shape, and that might mean that the frequencies aren't exactly 3 to 1. So let's now have a look at the perfect bowl, but with different frequencies. Let's keep this frequency the same, but slow this one down. Now we've got behaviour that's much closer to what we observed in the real bowl. It doesn't decay because in our perfect bowl there's no friction. And now we've answered our 3 questions. We can predict the straight line motions. They're given by the eigenvectors. And the general motion is given by adding motions along the eigenvectors, at least in the perfect bowl. And we can get some idea as to what went wrong in the real bowl by seeing what happens when we change the frequencies, when they're not quite as we planned them. Of course, it's very difficult to build a bowl of exactly the right shape. And that only goes to show, if you've got simultaneous differential equations to solve, it's better to use mathematics than to build bowls.